I'll trim the video to start here. 6033 in the news. I don't have a specific article, but the entire time that you're thinking about this lecture, if you want to think about the boat stuck in the Suez Canal as an illustration of what a queue is like, it's it's gonna work great. It's gonna work great. So we'll try to talk about the boat whenever possible. All right. So what are we gonna do today? So I told you all last time this isn't going to feel like part two of a two-part lecture series, but in some ways, this lecture is an answer to this question that I left you off with last week, right? So we talked about TCP last Wednesday, and we spent a lot of time talking about reliable transport, and then we also spent a lot of time talking about congestion control, which is just part of TCP, right? It's not at its own layer, it's part of that protocol. And the basic idea behind congestion control in TCP is that sources increase their window size kind of incrementally, right? They do this linear increase in many versions of TCP until they experience a packet drop, and then they cut the window size by half, right? And in some ways, you could TCP lives at the transport layer, but notice that it's actually using a signal from something that lives at the network layer, right? It's using a signal from a queue, namely a packet drop, to react to something. So we're going to see a little bit more of that today. All right, and so I left you with this question. TCP doesn't react to congestion until after it's a problem, right? Our TCP senders, they don't do anything. They don't back off in any way until the queue has already gotten totally full, right? They're seeing packet drops. And if you imagine, imagine a queue in a switch that could hold, say, I don't know, let's say like hundreds of packets, right? There's a lot of sort of congestion already present in the network. We typically don't want that. We don't really want full queues. In addition to eventually leading to packet drops, they also mean large delay, right? Like you're a boat stuck behind another boat, stuck at the head of a queue. All right. We don't like our queues to get full, right? But we do need queues to exist in a network. The reason that we want to have queues inside of switches is to absorb bursts of traffic, right? So if I'm a TCP sender and I send like, say 50 packets into the network all at once, but then, maybe I don't send any more packets for a few seconds. Like my application is sending out these bursts of traffic. That burst can move through the network just fine, most likely, right? It's kind of going to be all clumped together at the beginning, and then it'll start to be paced out by links throughout the network, right? And that's okay. We want that. We don't want our TCP senders to have to try to like get their windows exactly right or sort of paste their packets exactly in the right way. Like queues are a good thing. What we want from them though is to be what we call usually transient queues, right? So the queue data structure is there. It absorbs bursts when sources are, putting in too many packets, but then it drains, right? We don't want persistent queues. So those are queues that always have packets in them, right? Because if there's always packets in a queue, there's always going to be some added delay. Most likely, it's starting to build and build and build and build and build. All right. So what we're going to try to do is figure out a way to help our TCP senders respond earlier to congestion. All right. And to do this, we're actually going to move back down. All right, we're going to move back down to the network layer because we're going to let the switches take a more active role in this process. Right. So in this lecture, I'm going to go through a bunch of different protocols. Some of them address this question. Some of them deal with other things that we can have switches to do. So a lot of what we're talking about today is, what if we let our switches be a little bit smarter? What might they be able to do? And then really throughout this entire week, in today's lecture and in both recitations, you'll think about like, when is this applicable? When is this a good idea? All right. Now, if you want to do something fun during this lecture, how could you not? We're going to talk about all of these different protocols, and they all do a bunch of different things. I put this basically a PDF of this slide on the website. If you want to try to fill this out during lecture, that would be a totally nice way to kind of organize everything that's going on in this lecture. You don't have to, like, I'm not going to collect it. No one's collecting this. I'll show you how I filled this chart out at the end. But this is sort of how I've organized the lecture. And I thought, like, why not let you why not let you into that insight early? So people, if you're watching at home afterwards, you can do this too. All right. So this is on the website if you want to take a look at that. All right. So let's start. All right. So our first question today, and this is going to be directly related to everything that we've been talking about with congestion control, is given that we have a queue, when should it drop packets? And this might seem like sort of a strange question. And it might seem like sort of a strange question because many of you have probably only seen a queue behave in one specific way, right? You've probably seen queues behave according to a scheme that we know as drop tail, right? Drop tail says queue should only drop packets when it's full, right? And drop them from the tail, right? The tail of the queue. This is how we typically think of queues as working, right? You may have not even thought there were any other options, right? Now, there are some great things about drop tail queuing. It is as simple as it can be, right? Just let the queue get full and then start dropping packets. Super simple. It also only drops packets when it needs to, right? Which in some ways is nice, right? If our queues are dropping packets, that's going to lead to a retransmission. If we're thinking about TCP, we don't want drops, right? We don't want retransmissions. So, drop tail seems like a great idea. But some cons, one is just, the thing that we've already been thinking of. Well, drop tail is going to let the queue get through, or let the queue get full. Right? Is there something we could do to help with that? But then the second thing, which we haven't discussed yet, is that we can sometimes see a particular type of behavior. So I'm going to draw this for you right here in the middle. I'll make this a little bit bigger for this one. All right, so here's a queue. I'll move this so you can see it if it's not perfect right now. And we'll let this queue can hold however many packets that is, 8-ish. Let's say that it's not quite full, but it's almost full. Right, so it's got packets in all of these first 6 slots. Right, so here's one thing that can happen. A TCP sender comes in and it's going to send data into this queue. Let's see if this shows up. That could be darker. We'll fix that. Cool. Okay, so TCP sender shows up and it's got quite a few packets. It's sending one window all at a time and it's kind of bursting. So maybe it's got, it gets one packet into the queue here, another one, and then it was sending along like 4 other packets, but they all get dropped, right? There's just not room in the queue for them. So these are all dropped, right? That's fine. That's what we expect a queue to do. So, let's think about what this sender would do. It's got its TCP window set to something, right? But this is quite a lot of loss in the network. Most likely, this much loss is going to be resolved through a TCP timeout, right? So TCP times out, right? And you remember from Wednesday, when TCP actually times out for packets, what it does is it takes the sender's window size, drops it all the way back down to 1. Right, so we're gonna go back to a window equal to 1, and then the sender starts to increase from there, right? There's nothing wrong with this, right? That is how we design TCP. We said, if there's a lot of loss, we wanna throttle way back, okay? So this is not inherently a problem. Right, but let's think about what happens if we have a couple more senders come in, sort of doing the same thing. All right, so we'll see what colors show up. The different colors isn't that important. It's just fun for me, mostly. All right, so imagine now we've got a couple of different senders all bursting in here at once. Right, they're all sending packets into this queue. And, again, their windows, they could be set to whatever. They're just sending bursts of packets. All right, but they all come into this queue. Right, and again, some of them, there was a little bit of space in this queue. Some of them get their packets in, a few packets in, like I had this top sender get 2 packets in. Maybe the queue's got space for 1 more, the bottom sender gets some packets in. But ultimately, many of these packets here get dropped. right? So lots of drops from all senders, right? And these senders have nothing to do with one another, right? They're totally separate. Like you could imagine that this, this is three of you, right? You happen to be sending to the same bottom queue. You're not coordinating in any way, right? But there's lots of drops. This is going to lead to lots of timeouts, right? If these are all TCP senders, they're all going to experience a great deal of loss. They're all going to time out. They're all going to drop their window size back down to 1, right? And again, okay, that's what we told TCP to do. It's doing what we asked it to do. But here's what this means. This means that now these senders are starting to get synchronized, right? All of these senders, they probably had different TCP windows at different times, but now they've all experienced a timeout at roughly the same time. They're all dropping their window size back down to 1. They're all going to start increasing it at roughly the same pace, right? Depending on what their round trip times are. So you're starting to see this cycle. You're starting to see these flows all get synchronized, right? These sources, they all bursted. Packets got dropped from all of them because this queue was mostly full. There wasn't a lot of space. There wasn't enough space for one flow, much less all of these. All of the sources throttle way back. They have very, very small windows now, right? Which means now, if they're all sharing this bottleneck link, now it's going to be really underutilized. They're only putting, at the start, 1 packet per round trip time in, right? They'll start to increase, but now the network is really underutilized, sources will increase, and the cycle will repeat itself, right? So the fact that these flows potentially get synchronized from this type of queuing scheme, it's going to lead to decreased network utilization. This is not a great thing. We don't want to see this in a network, right? And there are a couple, there are some other sort of cons with this drop tail queuing. There's issues of fairness, right? Depending on how things go, your connections could just always end up hitting a full queue while other people's are getting through, right? Drop tail does lead us to mostly full queues, which is part of what we didn't want, all right? And if we see these kind of bursts of traffic, just super, super common on the internet, we can get this kind of synchronized behavior, right? So we're going to address all of these, all right? So the next protocol we're going to look at is known as RED, okay? RED stands for Random Early Detection or Random Early Drop, and it's a reaction to kind of all of these limitations, all right? Here's the basic idea of RED. Drop packets before the queue is full, all right? So drop packets even though you don't strictly need to. The goal is that this can give TCP senders an early signal that congestion is building. And if our switches can do this well, they don't have to be so aggressive with the drops. They can kind of spread them out, sort of, randomize them over all the different TCP senders. Hopefully we won't have that synchronized behavior. There could be a lot of good things, right? So this is an example of what is known as active queue management. The switches here are taking an active role in managing the queue. They're not just doing sort of something simple like drop tail, right? So here are the ideas behind RED. There's going to be a lot of different parameters. It is not my goal for you to be able to set all of the parameters exactly, right? And we'll talk about why that is in just a second, right? But the goal of RED, we're going to drop packets with increasing probability as the queue grows. So the fuller and fuller the queue gets, the more RED is going to randomly drop a packet. All right, so here's how it looks. I'm going to plot this graph for you. On the x-axis is the average queue size. So the average number of packets in the queue, right? We'll talk about how exactly RED calculates that average. For now, let it be whatever average you like the most, right? Average queue size on the x-axis. And then on the y-axis, the probability that a packet is dropped. All right, so there is some probability, if that probability is non-zero, every time it gets a packet, it flips a weighted coin, decides whether to drop. All right, so let's put some data in the graph. When the queue is really, really small, we're not going to do anything, right? No dropping. Probability of a drop is 0. It's fine. Let the queue, let the queue exist to some minimum threshold. All right. Now, once the queue exceeds a certain size, we're always going to drop. All right. So I've set these parameters, Qmin and Qmax, right? If you want, you can imagine that Qmax is like the actual maximum number of packets that the queue can hold. That's a fine model. There might be some specific cases where you'd want it to, for some reason, be smaller than that, but that's fine to think about that as the maximum size of the queue. All right, so the better question is, well, what happens in between? All right, like I said, we're going to increase the probability of a drop as the size of the queue grows. So red uses a linear increase rule, all right, up to some value Pmax. In some cases, Pmax might actually be equal to 1, right? In which case you would have kind of a nice graph like this, right? Instead of having this little step here, but there's nothing that requires that, right? And so Julian, good question in the chat. Are red packets dropped from the tail as well, or any entry in the queue? You can literally think about it as flipping a coin on every packet, right? So do I drop this packet or not, right? So in order to do this, right? In order to do this, the switch needs a measure of the average queue size. So averages are interesting. There's a lot of different ways to take an average. There's a lot of different questions about how you should do this, right? Do we average the queue size over the entire life of the switch? It could be years. Do we average it over the last 10 seconds, like 10 milliseconds? Like, how do we do this averaging? All right, so here's how red does its averaging. Make this a little bit smaller now. All right, so red does its average in the following way. And so, that so you can see it. All right, so that's going to be our average queue size, Q average. All right, the way it's going to measure this is going to take a look at, okay, at various points, the instantaneous queue size. That is the size of the queue right now. All right, measure it right now. Whatever it is, take that, multiply it by some value omega, right, and then incorporate whatever this was previously. All right, so this is just a weighted, like a weighted moving average. All right, and typically omega is quite smaller than 1. All right, so it does this nice weighted moving average. We kind of love to do averages in networking in this way. Big fan of that. Miller, I believe that red always does linear scaling, although you can certainly imagine, like, you could imagine changing this, right? You could imagine like I don't know, like a quadratic sort of scaling or something like that. That was a really good curve that I drew here. Oh, very proud of that, right? But I believe that red is always linear. Okay, so this is an interesting idea, right? And again, we're not going to get super into the details. Even this, I need to refer to this in 1 second, but we're not going to mathematically analyze this for a couple of reasons. Let me just tell you a few things. When red is working well, we see a lot of really nice properties. We see a much more stable queue length. So the queue length doesn't go from like very small to very large, very small to very large. And it's partly because of how this averaging is done, right? We typically, I mean, you can see from this graph, we also see, since there's a smooth change in the drop rate with congestion. So if the queues are full, we're not bothering it, or sorry, if the queues are almost empty, we're not bothering TCP senders, right? We're only doing drops sort of when we need to. And we do see flows getting desynchronized. We don't have that problem that I showed you with a drop tail, right? We don't have this issue anymore, right? And again, this is not a theory class. We're not going to do all of the queuing theory analysis. So you're gonna take that on faith, right? Now, these are all good things. We'll talk about the bad things in a second, except for one, because here's one kind of, I don't know, maybe almost glaring like problem with red, right? Why drop these packets at all, right? Drop packets still means that a source has to retransmit, right? So we can actually do something a little bit smarter. We've got the switches involved already, all right? So these are the good things with red. One thing we could do instead, take the packets and instead of dropping them, mark them, All right, so marking a packet refers to like setting a bit in a header, right? Setting a bit in the packet header. And if if the source noticed that a lot of its packets are getting marked, if it can take the same behavior, the same TCP behavior, that could be good. All right. So this is what a scheme known as ECN does. All right, same deal, but instead of dropping, we're going to mark. ECN stands for explicit congestion notification. So the way this works is, okay, imagine you're a packet. Normally I make you a switch. Now you're a packet. You're a packet, you're moving through a network. And at some point you encounter a switch, and the switch, according to this graph here, says, things are getting kind of full. I would like this TCP sender to back off a little bit. I'm going to mark this packet. All right, so that switch sets a bit in your packet header. You continue on through the network though. You don't get dropped. You get to your destination. All right, destination receives this packet. Now the destination isn't the sender here. They can't do anything except they send an ACK back to the sender. And the ACK is also going to be marked. So that ACK, if your sort of ECN bit in your packet header is set, so will an ECN bit be in the ACK back. So when the sender gets that ACK back, they'll say, oh, okay, one of my packets got marked, I'm going to back off, right? This is nice, right? This is a nice way to deal with this fact that, Red on its own is sort of dropping packets when it doesn't need to, which hopefully can make things better, but is a little bit unsatisfying. All right, but so given this, Red/ECN, they do have a lot of advantages over Droptail, right? Again, they give a signal when there is low congestion, right? It can lead to smaller persistent queues, which leads to smaller delays, less dramatic oscillation, in theory, less bias against bursty traffic. Bursty traffic is really, really common on the internet. So all of these are good things, right? But here's part of the bad things. And it's kind of one of the reasons why we're not going super far down this road, right? These schemes are more complicated and it can be hard to pick these parameters, right? So these things like Qmin, Qmax, Pmax, all of these parameters, they're sort of like optimal values depend on the state of the network, and the state of the network is always changing, right? So the best values for these parameters can depend on the number of connections running through the bottleneck link, the capabilities of the bottleneck link, all of these kind of things. And if they're not chosen well, they can make things worse, right? So neither Red nor ECN are like the final word on active queue management. You're going to talk about these protocols more in recitation tomorrow, and you're going to see other schemes, and you're going to see these queue management schemes applied to different types of networks, all right? Not just the internet. We're going to talk mostly today about what it's like to think about these schemes on the internet. All right, but now you have kind of a taste for this sort of thing, right? You have a sense of, hey, if the switches are a little bit smarter, we can do some interesting things, right? And that's really kind of the theme of today and even Wednesday's lecture and Tuesdays and Thursdays recitation, all right? So as long as we're here, we've moved back down to the network layer, we're dealing with switches, let's see what else we can do. We're gonna come back to queue management at the end, right? What else could we do? What could our switches do for us? All right, so we're gonna try a couple of different things. So here is the first thing we're gonna work on. This is a type of traffic differentiation. So suppose you have a couple of different applications running, all right? And one of them is an application that is very latency sensitive, all right? It needs small delays in the network, maybe something like Zoom. One is something that is not very latency sensitive, right? Maybe it's like Dropbox is like syncing your files, right? You talked about different applications having different needs, right? You talked about that when we talked about RON. So let's think about those kind of latency guarantees. Can we do anything, right? Can we do anything for that traffic that needs some amount of guarantees, right? So here's an idea. Let's see if we can get this to work. Okay, we'll make this bigger again. All right, let's again imagine that we have Zoom traffic and we have Dropbox traffic. All right, and here's one of our problems. Typically we're thinking, okay, we've got this queue in our switch, can hold some packets. All right. And maybe Dropbox is doing like a large file sync in the background. So you have a bunch of Dropbox packets. I will use D for Dropbox. All right. And then a Zoom packet arrives. If you only have one queue, right, we are serving packets from the head of the queue. We're not like going into the middle of the queue, right? It has to wait, right? It has to wait for all of these packets to clear the queue, right? It's stuck behind Dropbox traffic, right? It is the second boat trying to get through the Suez Canal right now, okay? It is just stuck. So, idea. Here we had one queue. Let's make a second queue. The Suez Canal analogy would be to dig another canal, right? So here are my two queues. These aren't the best rectangles, but you get it, right? I have two queues. One is for Zoom. One is for Dropbox. All right. Now I've added some work. All right, but here's the idea. My switch gets a packet. All right, packet. It inspects the packet, which is not a trivial operation. We'll come back to that, but it inspects the packet and it decides, okay, is this Zoom or Dropbox, right? If it's Zoom, puts it in the Zoom queue. If it's Dropbox, puts it in the Dropbox queue. All right, so imagine that, we've done that for a couple of packets, just so I have some things to point to, right? Now, as this is happening, we have an issue of scheduling. Before, when we were thinking about things like Red, ECN, Droptail, we were only thinking about a single queue, right? We didn't have to worry. Now we have multiple queues, right? There's a packet at the head of this queue. There's a packet at the head of this queue. Now I have a scheduling challenge, which is which packet does the switch send? All right. So here's what I will propose to you. We care about latency. So the idea that we're going to do is say, okay, if there's a packet in the Zoom queue, send it. Serve this queue first. All right. It gets priority number one. Right. So let's imagine that we do that. All right. So this packet gets sent. Right. Now there's no packet in the Zoom queue. Okay. Now we'll move to the Dropbox queue. We'll start sending packets from the Dropbox queue, but as soon as another one shows up in the Zoom queue, we're going to hop back to there and send it. If you want to think about this in like a more systematic way, you can imagine that, say, every time the switch is like kind of going through rounds and it's saying like, okay, is there a packet in the Zoom queue? If yes, send it. Okay, if it's not, send one from the Dropbox queue. And then it's asking the same question over and over again. All right, so we get some isolation here, having multiple queues. All right, this is known as priority queuing. All right, our scheduler was pretty simple. We said give top priority to this queue, second priority to this queue. But there's going to be some challenges, right? I can extend this idea to having multiple queues, right? I could have had like Zoom, Dropbox, and everything else. Okay, we could in some ways have a lot of queues if you'd like, but there's certainly an issue, right? I have, I've kind of drawn these where Zoom is only getting a packet occasionally, and Dropbox is doing this big file sync kind of thing. So there's only occasionally Zoom packets. What if there's all of a sudden a lot of Zoom packets, right? Or what if this is happening in a switch in the middle of the internet where a whole bunch of like Zoom connections are going through that switch, right? What should we do, right? There is certainly potential here for this latency sensitive traffic to starve out other types of traffic, right? If there is always a packet in the Zoom queue, we are always going to be sending that packet. We will never get to this other queue, right? And some of you might say, well, that seems fine, right? I gave the Zoom traffic priority. It is in some ways more important by virtue of being latency sensitive. Others of you might say, no way, Dropbox also matters, right? So we're going to come back to this problem. We're going to solve it, or we're going to address it today just in like 18 minutes, maybe 15 minutes. I don't know. You can time me, see what happens, right? So we're going to come back to that. But for now, hey, we're still in these switches. We can still do something interesting. right? And modulo this issue. Let's suppose we wanted to do what we'll talk about as bandwidth-based scheduling, right? Can we allocate specific amounts of bandwidth or sort of specific amounts of the network to some traffic, right? So think about what TCP was doing. We imagine for most of our TCP conversation, senders had infinite offered load, right? If there were two senders going into the same bottleneck, right? If like Karen and Sam were both sending into the same bottleneck, we wanted them to have each get roughly 50% of the capacity of that bottleneck. What if we want something different, right? What if we say Sam should get 70% and Karen should get 30%, right? Let's see if we can think of a way to deal with this, right? So here's how we're going to think about this, all right? There was a lot of enthusiasm from the O33 staff at our last staff meeting about Post-it notes. So O33 staff, I have prepared some Post-it notes for this. Okay, so you can't see them yet because I haven't put them on the slide, but you know, brace yourself. Okay, yes, amazing. We'll keep this in the middle. I'll move it around as stuff appears on the slide. So here are two queues, all right? We're gonna use, we'll let the bottom one be Dropbox because that's fine to stay. I'm gonna say Dropbox and Spotify just because I don't wanna confuse us with Zoom, which we talked about being latency sensitive, right? So this is my Spotify queue, this is my Dropbox queue. The numbers here represent packet sizes, right? Packet sizes can change. They don't have to be fixed. You can imagine these are bytes. That's a fine way to think about this, all right? But one important thing to know is that a queue will take a packet at a time, all right? Because it's data plus a header, it needs the whole packet, all right? So let's start with sort of a fairly basic case. This is like the base case, basically. Basically, all right? So suppose we want each of these applications to get an equal amount of bandwidth, all right? And I still have this problem of scheduling. Which queue do I send from, all right? The very, very most basic way to deal with this would be to use what we call a round robin scheduler, right? And this is something that, you know, you may have even thought about and just didn't give a name to, right? What a round robin scheduler says is essentially, okay, I'll visit Q1 and send a packet and then send a packet from Q2. And if there was a Q3, I would do Q3, then Q4. And then I would go back to the beginning, right? And do Q1, Q2, Q3, Q4, just sending a packet if one is there, right? So here I'd send Spotify, then Dropbox, then Spotify, then Dropbox, then Spotify, then Dropbox, then Spotify, then Dropbox, right? That is a round robin scheduler, right? Now, at its most basic, that's all it does, right? But you can imagine, you know, what if I wanted to say, I wanted my Spotify traffic to get twice as much of my outgoing links bandwidth as Dropbox? Well, we could do that by specifying some sort of weight, right? So this is not strictly like precise version of round robin anymore, but you can imagine what these would mean, all right? This says, okay, send 2 Spotify packets each round and 1 Dropbox packet, right? So we would go Spotify, Spotify, Dropbox, Spotify, Spotify, Dropbox. If we ran out of Spotify packets, we just clear out the Dropbox queue, right? That is the basics of a round robin scheduler, right? But now, suppose things change, all right? So instead of having a queue like this, right? Suppose now I have this, right? Dropbox starts sending a large file. Its packets increase from 10 bytes to 100 bytes through the magic of Post-its, right? Now, what is this scheduler going to do? The scheduler, as I've set it up, it's not taking these packet sizes into account, right? It's going to send 2 Spotify packets, right? So 20 bytes. And then it's going to send 1 Dropbox packet, which is 100 bytes, right? 2 Spotify packets, 1 Dropbox packet, etc. Right? So we're going to see, you know, I'm sending out 100 bytes of Dropbox traffic, the same amount of time that I send 20 bytes of Spotify traffic. That is not what I wanted, right? I wanted these weights to reflect actual like bytes on the wire, not just numbers of packets, all right? So we're going to try to fix this, right? Round robin doesn't work well with variable packet sizes, but Very simple. Okay, do not discount that. That matters a lot. All right. So next thing we're gonna try. We're gonna move up in our queue. We are gonna, no, we're not. We're gonna use the same cues. We're gonna try a scheme known as weighted round robin. All right. It's gonna let us deal with variable packet sizes. All right, so I'm gonna show you the algorithm over here on the right. And we're gonna go through the example with the algorithm, and then we're gonna kind of talk about why it works, all right? But you can kind of see, you can, in your head, probably imagine what we'd like to have happen here, right? I would love, given these weights that I'm trying to get to, I would love to send, say, 200 bytes of Spotify traffic for every 100 bytes of Dropbox, right? Another way to say that would be to say, okay, I want to send 20 Spotify packets for every 1 Dropbox packet. Weighted round robin is going to let us do this calculation. All right, so I am going to move this down a little bit. So I'm going to keep the same queue, all right? Same queue as before. I'll abbreviate so I have more room on the right. All right, so Spotify and Dropbox, right? I am still going to have weights, right? They're going to look a little bit different. We'll talk about why. 2/3 and 1/3, right? What this is expressing, I want twice as much traffic to go, or twice as much bandwidth allocated to Spotify as I do Dropbox. The weights sum to 1, right? So they're fractions now instead of integers. That's okay, right? I'm going to need some mean packet size, right? Mean packet size. In this example, no problem. 10 and 100, right? I don't have to worry about complicated averages at the moment. Take 10, 100, all right? So what am I going to do? How does this algorithm work? All right, so what this algorithm says is for each round, so sort of each time we're going through the queues, we're going to do this calculation, all right? We're going to figure out the norm, all right? So the norm of these two things, all right? So I will just remember Spotify, Dropbox, right? So this norm, right? We can do the math, the weight over the mean packet size, right? So 2/3 over 10, 1/3 over 100. These are not going to come out to like wonderful numbers, but it's fine. We can do this. We can calculate this norm, right? The next thing it's going to ask is, okay, well, which of all of these norms, which is the smallest, all right? That's also, we're certainly capable of doing that, right? That is our smaller norm of the two. And if we had more than 2 queues, we'd be doing this, no big deal, right? So what do I do with these numbers, right? Well, I'm going to look at each queue, right? And I'm going to figure out, well, how many packets do I actually send, right? It's whatever this norm was over whatever the minimum of the norms was, right? So in this case, again, it's not, it looks messy, right? 115 over 1/300, right? But it's fine, that's 20, right? That's my n packets. 1/300 over 1/300 is 1, right? And if you remember, this sort of matches our intuition, right? We want to send 20 Spotify packets for every 1 Dropbox packet. So this algorithm, it does that math for you, all right? This so far is great. Yeah, there's fractions, but it's fine. Fractions are fine. Okay, so it seems like it's going well. Let's make things a little bit more complicated, all right? To make things a little bit more complicated, we're gonna move up, right? We have some slightly more interesting packet sizes now, all right? So what are we gonna do with these? I'm gonna keep the same weights, right? So my weights are still 2/3 and 1/3. I still want that kind of same outcome, right? Wait. My mean packet size, now it's getting a little bit more complicated, right? And you can imagine that averages are challenging, but we'll take an average of what we have going on here, right? So mean for our second queue, the Dropbox queue, still easy, it's 10. Here it's 8 1/3, right? Again, that's fine, right? We can do the same math, all right? We can calculate these norms You can do this at home, fun for everyone, right? The fractions, again, they're quite messy, right? But we're gonna do the same math. We're gonna find, again, this is our smaller norm of the two. And what does this work out to? All right, well, for every one Dropbox packet, we're gonna send roughly 2.4 Spotify packets. So, okay, maybe sometimes we send 2, sometimes we send 3, we try to average out. But you know, sometimes 2 packets will be 20 bytes, sometimes it would be 15, sometimes 10. This is starting to get less precise, right? And I haven't even sort of gotten to the issue of, well, how do we actually calculate this average packet size, right? Over all packets ever, over the last n packets, the same way we did for red, all right? This is a problem. We're not gonna solve it because we're gonna skip it entirely, right? So we're gonna move to our final algorithm, right? So needing to know the main packet size, that's challenging, right? We're gonna go to the algorithm with the best name, deficit round robin, right? I am gonna just cover up that word for a second so I can do one last example. I will uncover it when we're done, right? So we'll take this same exact queue, all right? The same thing that we were doing before so that you can see it there. Now you can see, all right? What are we gonna do here? So we're gonna try to go for the same thing, basically twice as much Spotify traffic as Dropbox traffic, all right? We're gonna express this in a slightly different way now, right? Instead of having weights of 2/3 and 1/3, I'm gonna have quantums. See, it's cool names all the way around. I'm gonna use a quantum of 20 and 10. We could have used 2 and 1. We could have used 200 and 100, right, for what we want. You will see some benefits and drawbacks of those as we go through, but 20 and 10 is gonna work fine for us. All right, so here's deficit round robin. I enjoy this algorithm the most, right? So in each round, we're gonna look at each queue, and we're gonna keep track of some credit for each queue, right? Credit starts at 0, right? No queue has any credit, but each round we add, right? So whatever this quantum is, that's the amount of new credit each queue gets in each round, right? So now we've done 20 and 10. And then we're gonna send packets until we deplete all of the credit. All right, so we'll look at Spotify. Okay, the first Spotify packet here is 10 bytes. We're gonna go ahead and send that. All right, that would knock our credit down to 10. We still have some left, and hey, it's enough to send the next packet. So we're gonna go ahead, we will send that. And now it's 0. All right, I'll write that darker so you can see it. All right, now we're gonna do the same thing for the Dropbox queue. So the quantum, we set that. The switch operator sets that. I'm saying it's 20 and 10 because I want a 2-to-1 ratio of traffic. All right, my Dropbox queue has a credit of 10. That's enough to send this packet and no more. All right, then we keep going. All right, so I'm gonna add credits back to everyone. All right, this is basically saying how many bytes of credit have I accumulated? And if I have enough to send some packets, I go ahead and send them, right? In this case, I could send 5, then 5, and then 10, and I'm back down to 0, right? In this case, just send 1 packet, right? Now, I am gonna leave one example for you all to do at home, right? Because this credit will carry over, right? For instance, if my next Dropbox packet, say things changed, and this packet were 20, I would not accumulate enough credit in the next round to send it. It would take me 2 rounds before I sent this, all right? This is really nice. It's really nice. It's really good. We don't need the mean packet size. This gives us near perfect fairness. We won't prove that, right? But it's very good. It's low processing overhead. Typically, schemes that get you even closer to perfect fairness are less reasonable in practice. Deficit round robin, honestly, is pretty good. Right, so these are all different ways that we can think about I'm doing this bandwidth-based scheduling. And now that you know that, let's go back to something that I left undone before, right? I left this issue of sort of, you know, latency sensitive traffic potentially starving out other types of traffic, right? Now we can think about how to deal with that, right? I could, for instance, have my Zoom queue up here, my Dropbox queue down here, and think of ways to say like, okay, yeah, serve this queue first, but limit it to 30% of the bandwidth, right? I could start to combine these things, right, to try to make things more fair for everyone involved, right? Miguel, is it better to have a lower quantum versus a higher quantum? So great question. If your quantum is very small, it will just take you a lot of rounds to accumulate enough credit to send a packet. If the quantum is really, really high, then your short-term fairness is not going to be as good. You're going to send like 2,000 Spotify packets and then go over to the Dropbox queue and send a bunch of Dropbox packets. All right, so it's nice to have it sort of reflect the actual packet sizes that are realized in practice. But in terms of like correctness of the algorithm, you know, we'll get over long time scales, we'll get what we want. All right. So the question I want to leave you with. All right. So first of all, I'll show you, this is my answers for what we did. As you can see, deficit round robin, honestly pretty good. You can check those out, all right? I want to leave you with a different question though. I want you to think about something. Is this a good idea? Is any of this a good idea? So I have a question for you all. Well, I have a bunch of questions for you. Oh man, we could do questions all day. So here are some questions. One issue is just what granularity of isolation in these queues makes sense, right? Figuring out whether a packet belongs to Zoom or Dropbox is not actually particularly easy, all right? That can be a very, very hard problem to do. One other thing, and here's the thing I'm interested in, there is not a correct answer here, right? Think about these priority queuing schemes. Who should decide? Who gets to decide what traffic in the network gets priority, right? Should you or I get to, should I get to decide? Should ISPs get to decide? The government, nonprofits, right? Someone has to make a decision in these types of schemes about who actually, who's most important, right? That is a complicated question. And then imagine hooking all of these things up together, right? So say I'm a switch, I'm connected to Karen, who's also a switch, and then Sam, and then Wesley. We all maybe have different priority queuing schemes, and we have prioritized different types of traffic. What's going to happen end to end, right? What happens when all of those switches interact with each other? And in fact, we could have asked you the same question when we talked about TCP. The TCP congestion control scheme that I showed you in class is sort of one of the like original schemes. There are some updates now, some slightly different, you know, increase decrease rules. Thinking about how those fit together is complicated, right? So there's kind of a larger question that we're getting at here, which is, you know, is this a good idea on the internet, and who should make what decisions, right? There is both a question of what people should make decisions, but there's even a question of what components of a network, right? Should the switches be involved here, or should we think about certain functionality only existing at endpoints, right? That is a big question in networking, right? You will come to wrestle with that for the rest of this week. It's the kind of the one of the topics of the paper that you're going to read for Thursday. But in terms of the question I started out with, we can get senders to react before queues are full, certainly if switches take a more active role, right? But making that happen is challenging, and there are a lot of questions unanswered. So I had no idea what you all would say as a result of this poll, but I can say, you know what, I'm just going to share the results as all anonymous. So people are least excited about the government, but second least excited about the 033 staff making these decisions, which, come on, I think, I think we're very good people. Yeah, not allowed to check now. That's fair, Derek. I did force you to make a choice. It's a good question. I don't have an answer for you, right? But it's an important thing to think about. So I'm gonna stop sharing. I'm gonna stop recording.